Any luck? Hold on. Looks promising. Yes.
Well, thank you so much for this introduction, Tom. And I want to start by expressing our gratitude for this support from the Academy of Neuroscience for Architecture. We spent a year together, an architect, a production designer, and a scientist, pondering the future of design of built environments from the three perspectives. I'll briefly introduce the team, and then we'll delve into details into our respective approaches. Alex McDowell, he is a professor of art practice at the University of Southern California School of Cinematic Arts and Division of Media Arts and Practice. He is one of the most influential designers working in narrative media, with the impact of his ideas extending far beyond his background in cinema. He has over 30 years in experience in narrative design, and most recently he spends his energies on advocating an immersive design process and the key role of world building in storytelling. Greg Lynn is a professor of architecture at UCLA, as Tom mentioned. He's the owner of Greg Lynn Form architecture firm. He is a practicing architect, and he is best known for redefining the medium of design using digital technology. His interests include dynamic or kinetic architecture and fabrication of complex ergonomic forms using numerically controlled machinery. And I'm a vision scientist here at the Salk Institute. I study visual perception, interaction between first stages of the visual process with other sensory modalities. And before long, I will briefly define the scope of our research, and then we will each talk about our approaches. We thought that it's easier to define the problem by first sort of capturing the state of the art in the field, and then looking at our respective approaches to the next steps from our newly emerging sort of synthetic view of the future of design of immersive environments. From Alex's perspective, the present is defined by visual narratives, which are screen-based, where the spectator is static. For Alex, the urgent question in design of virtual environments is how to turn the screen into a window and let the audience enter the space behind the screen, how to break the screen. For Greg, the present is defined by architectural practice, which has developed excellent insight into the spatial character of buildings. What is lacking, from his perspective, is an equally advanced insight into the dynamic character of built environments, their perception by moving observers, which is particularly demanding when the buildings themselves involve moving parts or moving pictures. From my perspective, I would say we know a lot about perceived structure of the environment measured in the image plane. We have a comprehensive understanding of spatial temporal interactions between patterns in the image plane. Now, there's a question of whether our understanding generalizes from the image plane and to the space. If it did, then we would have established a launching pad for a comprehensive understanding of perceptual space. So the goal of this project was to test this prospect of mapping the space and looking at what possibilities this mapping would afford for the future of architecture. And with this, I will give word to Alex McDowell. Switch to the next slide.
Yeah, good. Thank you, Sergey. I must say I feel completely out of place in this illustrious company as a media maker, but very honored to be here. My background was was sort of formed in this space, this 20th century cinema space, where the audience, although deeply immersed in the narrative, in their imagination, has a static relationship to the screen-based media. I've moved sort of into the cinematic arts space at USC and come into contact deeply with the interactive space, but nevertheless, I still feel like this is a fixed relationship of an audience member with a screen. So as my kind of process in film developed, it became clear that new technologies were opening up completely different ways of immersing ourselves, first of all as practitioners, creators, as authors, that we have an opportunity with new media to, or with new tools really, to completely immerse ourselves in the design space. I've got it actually. So in this design visualization kind of track in the center here, we've spent a lot of time thinking about the ways in which you can prototype the creative process and starting with the point of imagination, and as creators getting deeply involved in that creative space as the first users, and really focusing on how we begin to actualize the imagination with all of these new tool sets. So prototyping becomes a kind of crucial component and an increasingly enlarged component. We're looking all of the time at the role of the participant in the narrative space, so whether they be Oompa Loompas or the characters in Minority Report, but also the tools. So this was a unique piece of pre-visualization where we were using an industrial robot, a giant camera, and driving it with somebody who's only normally used to moving that crane around in real time, but doing all of our planning in a very complex environment in the virtual space. Also in Minority Report, we kind of discovered the enormous benefits of storytelling in a predictive sense. So literally, precognitively, this young man, John Underkoffler, who came to us from MIT Media Lab, engaged in a design fiction during the film. This fictional interactive media, the G-Speak that he ultimately made for real, was first a complete fiction, and then in the film it became expressed, and then there was a sort of demand for its actual existence, and it came into existence. So we're sort of continuing to think deeply about how this prototyping space allows us to have a new interaction with the participants and the occupants of the narrative container. In this case, in the terminal, something that resembles architecture clearly is not architecture, but is absolutely a container for the narrative, but again, prototyped extensively for a very large-scale piece of construction. In the school now, we are conducting a number of experiments in the World Building Media Lab. This is a vast collaboration of an imaginary city called Rilao, which is formed from the chance encounter of Rio and Los Angeles meeting on a small island in the Pacific. But really thinking about the ways in which, in this case, about 120 students across 7 schools around the world can all dive into a collaborative workspace. And what tools do we need, what processes and what new forms of work do we need to evolve in order to be able to work not only in the virtual space, but also in this case from Behnaz Fahari, who is one of our research students on this project, prototyping in the real world. And then our sort of longest term project has been this Leviathan, which is a giant flying whale set in 1895 with a payload of 70 or 80 characters flying from London to Moscow. The idea here is that it's a completely self-contained ecosystem, and again, really deeply looking at the ways in which we collaborate and we practice in a new relationship to what is increasingly, I think, resembling architectural space, that we're actually moving around in the built environment, albeit virtual. In this case, Bruce Bloch, who's one of the founders of the cinematic narrative in the film sense, and has been teaching that for 30 years, stepping into the completely virtual world and finding himself incredibly excited by the possibilities. But what we're discovering is a deep need for developing a completely new language for this kind of space that is a window rather than a screen. This project was developed not only in the virtual world, but in the full VR, but also in augmented reality. In this case, we took a kind of cinematic approach to breaking the screen plane completely, flying a giant whale over an audience of 5,000 people with no devices between them and the virtual object, but capturing it in 5 live cameras. And then that same experiment extended on different scales, so the tablet becoming an interface as well as the screen itself. So you have, if you remember back to the first image I put up, no longer a static audience sitting and staring at a screen, but a highly interactive and very participant audience now fully engaged with the environment around them. And although this is a kind of whimsical framework for this serious research, it speaks directly to what we're doing. So in the project itself for the Hay Grant, I think what's been incredibly interesting to me has been this very cross-disciplinary collaboration between the perception space, the narrative space, and the environmental architectural space, and the absolutely interlocked relationship between those different elements that story evolves out of and the experiential space evolves from in a kind of deep way. So thank you. Do you want me to change computers?
Master computer.
Okay. Great. So to kind of get into what we did with the grant a little bit, I've got a kind of a preamble, and I would just say that today a lot of the discussion has been about the media of architecture, meaning mostly space and volume, but also texture and sound and smell. And instead of that media, I want to talk a little bit about how architects design and the mediums that we've used in the past and that we're using presently, only because I think when Sergey and Alex and I first started talking about the grant, it was very clear that we wanted to make a bridge between a scientific approach of vision science with a narrative approach to multi-point, multi-person experience to an architectural approach that connected with our medium. Because I think the way to get architects excited about science is not so much to give them lectures and teach them things, because I teach architects and you don't want to be involved in that business, I doubt. But what we get very excited about is when you give us tools and new mediums for us to start to work with, and if those have some scientific intelligence built into them, all the better. I think one thing that goes without saying is that architects tend to be this strange combination of very nerdy, geeky people invested in measurement and geometry. We also tend to revert to discussions of intuition, where things get very loose, very personal, very unscientific, and frankly often very delusional and incorrect. I think architecture, not just for architects, more actually for everybody else, is a field dedicated to stasis and statics. People think of architecture as being timeless. It's okay if you work in a building or live in a building that's very out of time with the rest of your contemporary life. You accept that in architecture in a way you don't accept it in a cellular device or something. And the field tends to think in statics, but when people talk about it, they talk about it in statics. And one of the things I have to say I'm surprised by is how discussions of images and perception and repetition only work, those arguments only hold up if you accept a static viewpoint. That one moment where the sunset aligns with the fountain and the eye is low enough that you can't see the horizon, and there's one point where the Salk Institute works perfectly, and it works twice a year for a few minutes, but that's the picture everybody uses. And so one thing that I know about architecture is we're dealing not only with tens of thousands of elements that need to be put into an arrangement and organized, but we're also organizing big numbers of people that don't really like to sit still and that experience architecture while they're moving. But this model of the fixed eye and of the perspective has really held sway in our discipline, and I think it's more than just a technique. I think it's a whole sensibility, and I would just say back to vision science, as much as you can get away from this static optical point where you're clamping people's heads to desks in front of screens, the more excited architects are going to get, because we don't think of people as these static eyes. We think of them as crowds and collections, and we think of them in motion and in movement when we're working our best. So in the same way we deal with large numbers of elements that need to get organized, we like to think of large numbers of people that are moving in many different positions. I think one way to connect with architects is to connect with their rigor and geometry and measurement side of the field, and to attack what always becomes the intuitive arguments about, I know how the space is going to feel from my experience, or I know how it feels from the medium I'm using. I'm not saying you're going to get architects to want to go post-occupancy measure how people feel in their spaces, but I think if you can appeal to the dimensional geometric models, you'll get a lot more traction with them from the perspective of vision science. This is a picture of Mies van der Rohe in front of a model. I would just say that today, architects work more creatively in a physical modeling space, and it maybe just needs to be mentioned that we tend to scale visual experience and spatial experience. I have no idea what that means in terms of the neurosciences and vision science, but we assume we can scale things down and put our heads in models and move around in things and replicate some of the qualities we're looking for at a much larger scale, at a small scale. But this scaling effect is how a lot of architects work with space. And it's really not black magic the way some architects would tell you that it comes from some intuition privately. It's tested. It's usually tested in physical models. Historically, drawings were where ambiance and texture and light would get expressed. What I've seen in my lifetime is a shift from those kinds of drawings and these kinds of models. This is a Brunelleschi model. Since the Renaissance, architects have worked in huge models, not just for structure, but really for spatial modeling and spatial character. Certain architects, this is Frank Gehry's Miami World Symphony Concert Hall. You know, all those people are little lead people that are probably 1/4 inch scale, so it's like a 15 or 20 foot model. To study the characters of the space, and those images are physically projected onto surfaces of the model. Some architects still work in big models. I personally always design in large models. But dominantly, the field has shifted towards moving cameras. So the technology for pre-visualization and special effects from the film industry has replaced a lot of those drawings and a lot of those large models, and you're seeing more and more architects doing fly-through, fly-over animations. And one of the things that I find most troubling is that what could have been expressed in a drawing or a diagram often ends up becoming a 2-minute animation, and that animation isn't really showing you anything. It's got a lot of kind of mindlessness and to it, and not so much intelligence. So one of the things that we're trying to do in this grant is look at animation and motion and those technologies in a way that's very intelligently perceivable and also measurable and reproducible. Just a couple of cultural changes that have happened in the field before we go to Sergey and the experiment. I think the first is that 20, 30 years ago, large-scale moving images started to become ubiquitous in certain cities. And more you see large moving images covering surfaces, even sitting in an augmented way between us and the spaces we're in. I think architecture was very sophisticated and very fast about how to integrate those kinds of images into everyday spaces. But initially, they were done for their spectacular value, like this image at Times Square. The new spectacular buildings are, instead of looking at these large-scale images, which I think pose a problem to vision science and architecture to conceptualize, there now already is this whole genre of giant robotic buildings with huge moving components. So in the case of this 200-ton stage in Las Vegas in the Cirque du Soleil Theater for Ka, designed by Mark Fisher, you have a giant robotic platform that works as both a projection screen and a stage. And I mean, it's an incredible large-scale, spectacular piece of robotics. It costs $250 million, so you don't see them everywhere yet. But the idea of a moving transformable surface you're seeing in more and more places. This is 12 years old, I believe. The Culture Shed in Hudson Yards in New York, which is under construction, designed by Liz Diller and David Rockwell, is a huge event and performance space that rides on cargo shipping rails and opens and closes on a weekly basis throughout the year. So when it packs up tight around that museum, that's all an open outdoor space. It can telescope out and unfold, and you can have a 5,000-person Fashion Week event or something like that. And it's done not for function as much as really for the spectacle of this transforming building in New York City on the waterfront. The Prada Transformer by Rem Koolhaas is this four-sided building that comes with 4 construction cranes, which you don't see in this photo. But every month, the 4 cranes would pick it up and roll it over onto a different facet. So as it was first in Seoul, you would see this building get rolled every month, and you could experience it a different way every month. But so this is just to show you, I could give you a 3-hour set of examples like this of how architects are looking at motion and robotics in buildings, and it's a kind of maybe happy byproduct of some of the things we've been studying. Because of this development, when I started teaching at UCLA 18 years ago, we were the first school of architecture to get big-scale, computer numerically controlled fabrication equipment. It was very unique then that you'd use a robot to be a carpenter or a bricklayer. I'm bored out of my mind with it, and every university on earth now has robots building things. And so a couple of years ago, we decided to take this initiative to look at moving rooms and start to build moving walls and moving floors. And we set up this facility in the Howard Hughes aircraft hangar with a couple of big robots that can lift big pieces of stuff. And here you see one of the screens we made, especially for the grant, in that robotic setup, which we can, most importantly, we drive all this very easily with a piece of design software. I mean, our partner is Bot and Dolly, which was that image you saw of the illusionary screen. But we can move these robots around just by dragging a mouse on screen. We don't have to have an engineer set up that motion for us in the interface. So what we're able to do is, in a measurable and repeatable way, reposition very large-scale pieces of building in space. We're able to sync that with moving images, and we're able to do that in a very synchronized way. And so that's really where our grant began, was with that ability. And Sergey and I still, I don't know who owes who dinner, But I think there's a big difference between a moving image and a moving image. And what our grant was all about was taking a standard test in neuroscience and vision science and applying that moving image not to somebody with their head clamped, but in a room where it could be synchronized with a moving screen. So. I hope I didn't go long.
So this is the space in which we did our research, and the unique environment that Greg built at UCLA. To start describing our experiments, microphone. Thank you. To start, I want to make a very simple observation. When you look at any scene or photograph of a visual scene, you will experience different density of visual information in different parts of the scene. So look, for example, at these two parts where the density is relatively low, so the spatial distance between parts, visual features is rather large. In other areas, the density is higher. This is sort of a universal observation about anything that you would look at, I believe. In vision science, we address this by dividing images to elements. So we could think of them as atoms of visual of images, and they're called luminance gratings, where the amount of visual complexity is fixed. So here is the fixed density of visual detail, which means that the number of features, these vertical white bars, is constant per unit of visual area. We call this dimension spatial frequency. Here it's low, where there's a small number of features per unit, and here it's high. So the spatial frequency is the dimension that has to do with increasing, in this case, increasing from left to right, density of visual detail. We can tell a lot about our visual abilities by simply varying spatial frequency and contrast. Here's low contrast and high contrast. For example, we measure the boundaries between visible and invisible by finding the amount of contrast that makes some image just visible, which is called contrast threshold. One of the very basic ideas in vision science is that the visibility of patterns depends on the density of visual detail. Here is one celebrated illustration of that, created by Campbell and Robson yet in the 60s. Here they varied this density of visual detail, called spatial frequency, from low on the left to high on the right, and contrast changes from low to high. And you may see that if you try to determine where the boundary is between the visible and invisible, here this position will be lower than here, and here it's low again. So as we vary spatial frequency and contrast sensitivity, and contrast in this image, we may recover what is called a contrast sensitivity function. It's a function of threshold across density of visual detail. So to simplify things a little, instead of talking about functions, we could talk about just the range of the amount of detail which is visible well. So very, very slowly changing luminance patterns are not well visible, and rapidly changing ones are not well visible. In between, there is this region which we may call a window of visibility. This is just the range between moderate values of the density of visual information that make the stimuli well visible. What we do in the laboratory is what Greg described gracefully as a clamped observer. It's a fixed distance, usually between the observer and the screen in a dark room, where we present these patterns like these drifting luminance gratings, and we ask them on every trial, and there are many trials following one another, whether the stimulus, the image, was moving up or down. And now, to translate this map into space, let's make this very simple observation that if you take a fixed pattern like this, with this fixed density of visual features, and move it away from you, then in the image view, the frequency or density of visual information will increase from left to right, which means that this mapping across spatial frequency or density of visual detail applies to distance. This is key to our transition from the image plane and into space. Now, what I just showed you, taking an image at a fixed pattern, sort of painted on the surface, and moving it away from the observer, it amounts in this space to this change in distance and spatial frequency, change in the density of detail. So essentially, for any pattern, you could find an equivalent pattern that would be just as visible at a different distance. What I described before as a window of visibility, this gray region here, the middle region where things are visible well, it will help us to understand how our insight into the boundaries between visible and invisible in the image plane translate into space. So if I take this image and move it away from you, it will change from invisible to visible for a coarse pattern, for low density of visual detail. And here on this end, where the density is high, a pattern would be visible here and then become invisible. So things would move in the window of visibility and out of window of visibility as we move them in space. Does it correspond to your intuition? So consider this case when you see something at a distance, maybe some poster, you don't really make out the print. If you get closer to it, or you move the poster closer to you, shorten the distance, it will enter the window of visibility, which corresponds to our intuition. As we get closer to things, we see them better. But if you consider a low density pattern, if you start somewhere here where it's well visible, and you get closer to it, it will exit the window of visibility. You will not see it anymore. This is not as intuitive, but this is a very basic fact about the visual system. And this is the beginning of our mapping the space in terms of what is visible and what is not. So our approach was twofold. First, we wanted to measure contrast sensitivity at two removed distances using this machinery that Greg built by presenting these gratings at large screens at the distances that correspond to the scale of architectural spaces. We'll measure sensitivities, contrast sensitivities at these two distances, and then we'll try to probe the space in between and see if our understanding in the image plane translates into mapping of space, into the solid regions in space which define what is visible and not in different parts of space. So here is a summary of our methods for the first series of experiments. Again, as you saw before, this is the distance. Observer is here somewhere. Spatial frequency corresponds to density of detail. These are the patterns that correspond in terms of density of detail as you move them away. The black and red dots represent the measurements we made at one near distance and at one far distance. And we used the same approach we used in the laboratory, just the screens were large and the whole space was enormous from our traditional perspective. Very briefly, we used drifting luminance gratings. The task was to tell whether the gratings were moving left or right. They were presented for half a second. They were projected on the screen at a fixed distance from the projector to remove the confound of variable luminance. The system was gamma calibrated. We used the so-called noisy bit enhancement of contrast resolution to make sure we have enough precision in the contrast domain to capture sensitivity, contrast sensitivity of human subjects. Our procedure of measurement was so-called adaptive staircase. For each condition, we started from very high contrast and we gradually reduced them to find the contrast threshold, the amount of contrast that makes these drifting gratings just visible. So here I am rotating the space to show you results. This is just to indicate that what we found is something expected from our knowledge of vision from the image. from the image plane. Here's the distance again, the amount of density, and this is sensitivity. The higher the sensitivity, the lower contrast is necessary to make the stimulus just visible. So these two distances, we measured the two contrast sensitivity functions. Now, let's consider this in some detail. Again, these are the conditions which are equivalent in the sense that if you take a pattern and move it away from you, it will increase in the amount of visual detail in the image. So consider, for example, this high density image, moving it closer to you, as I discussed before. So it would be invisible, almost invisible here, and then become more visible. But at a lower grain, at a lower density of detail, it would be first very visible and then less visible, that paradoxical example that I mentioned. To appreciate that, I replot these results now in terms of the size of the grain, which is called grating period, the size, sort of the distance between the features in the image. And what you can see here is that indeed, when you decrease distance to a pattern going from far red to near and black, indeed, a fine pattern becomes more visible as expected, but also a coarse pattern becomes less visible here, where the distance is large between the features. This is the coarse pattern, and it becomes substantially less visible by a factor of 4 here. Notice that even this very simple study suggests that there are regions in space where joint visibility is possible. That is, you could divide the space between you and some large structure to 3 zones, where features, large scale and small scale features, are jointly visible, and here only features at the small scale are visible, and vice versa. So here is the beginning of our understanding of how the space is divided to the solid regions. It's divided by these invisible, unseeable walls. And as we move through the space, or there are moving elements, this space is sort of breathing. We move, we cross these invisible walls, or the walls are moving towards us if the building environment involves some sort of dynamic imagery, moving pictures perhaps. So the summary of the first experiment is that essentially we were able to map contrast sensitivity for 2 distances on a large scale. We validated predictions of contrast sensitivity, and it was the first glimpse of mapping out solid regions of joint visibility. And then we get to a more interesting part of this project where we are beginning to actually map out space using these robots. So the subject would be seated, for example, and the robot would move the screen towards the subject, revealing these boundaries between visible and invisible in space. This is actually an example of a trajectory of a robot moving across distance, several meters, and presumably going from the region of visibility to invisibility, crossing this boundary here. This is sort of a vanishing point. Vanishing point where subjectively the pattern disappears, even when the pattern doesn't change on the screen. So this vanishing point should also depend on dynamic content of the image. I have not mentioned that yet. Here is a simple illustration of how it works. Now we are looking not at a static pattern, but on a dynamic pattern, say a moving picture on the screen. And again, it's moving away from you, so the density of spatial detail increases. But also notice this is the function I showed you before. We know from our extensive studies in the image plane that when you induce some motion into these images, your sensitivity increases more so at near distances than at far distances. A complete map of that. Here, let me just map it out in more detail. So this is the window of visibility for static image, shown in red. And in blue is the window of visibility for a dynamic image. Notice that this space, this boundary between visible and visible, it's remapped. This boundary is shifting towards you, as if by adding some dynamic content into your structure, you open up certain zones, certain solid regions in space to perception. So you bring in new perceptual valences into space by adding, by titrating the amount of dynamics in in the built environment. So this is how this looks from our perspective. Here's familiar to you spatial frequency, density of detail, and this is temporal frequency. As we vary the amount of motion in the image, we can increase the window visibility from here to here. See, this function becomes higher and it opens up to the left. This is another view of the same thing in more detail. It's called spatial temporal contrast sensitivity function. Here you see the bird's eye view of this function. This is amount of detail in space. This amount of detail in time. It's measured in hertz. It's the number of sort of features repeating per unit of time. And the color here represents the sensitivity. So you are more sensitive in this region, which means that for patterns which are close to you, this window of visibility is relatively narrow across the amount of spatial detail. As you add temporal detail, it opens up. This window becomes substantially larger. So broadening of the window visibility towards lower density of spatial detail is expected from our perspective, which means that as you move this screen by the robot towards you, the window is supposed to move towards you to closer distances from here to here. Okay, and this is an example of how we did this experiment. The subject looking at the screen, approaching, moving back and forth. Here I show it in more detail. So in this case, we used the approach called direct report. The subject was watching the screen moving in and out. So this is far point. The screen would move in and out and do 3 excursions of this kind. The computer would issue a prompt every second. It was a sort of 1 hertz sampling of experience. The task was to tell whether you see the pattern or not. And then we integrated, these are the actual moments when the subjects responded. That's why it's slightly irregular. And then we just integrated the fraction of visible responses for each sort of band, for each distance band. And here is an example. So to remind you, we expect as you get closer, as the screen gets closer to you for coarse pattern, it suddenly becomes invisible. And here is the result for one subject, for low contrast, for very low contrast of the image. As it's easier to understand here on the dimension of distance. Remember, distance and density are correlated. So as the screen gets closer to you, visibility decreases for both contrasts. We were able to, this way, we were able to test our predictions from the measurements at 2 distances and across the volume. Here is where we predicted from the first experiment, where we predicted the vanishing point, and that's exactly what we found. So we discovered this very nice correspondence between the measurements with dynamic and static screen. And finally, as you add temporal content, as you make the stimulus move faster and faster from blue to red, you see how the point where the stimulus appears moves towards you in distance. Here it moves closer to you, which means that the space is opening up for new perceptual possibilities. And to summarize, we sampled sensitivity across viewing distances. We made first step in mapping the space proper. We found stations between zones of visibility which follow a predicted pattern, both for vanishing locations and for shift of the vanishing location with varying dynamic content in the image. This way we have accomplished this proof of concept. We developed a suite of methods for mapping solid regions of visibility. We implemented a measurement platform for this mapping. And this way we are prepared to do the next step. All these results will be published on the ANFA site as a technical report. We are preparing a couple of publications. We are looking into new finding possibilities. This was a seed grant. Using the new measurement platform, we are going to apply for larger funding. The applications of this are numerous. Here we mentioned just a few. It's case studies in architecture and urban design, in virtual architecture, immersive media, immersive cinema. And I just want to thank the larger team. It's Brad Newman, Derek Passmore, and Binas Farahi at USC, and Guven Chozel, Peter Vikar, Yulia Kerner, and Ibrahim Pustinci at UCLA. Thank you so much.